We looked last time at a particular protocol for proving quadratic residuosity, and we showed that it satisfied completeness and soundness, and we left off with the claim of zero knowledge. What we need to establish and understand that claim is to actually define what zero knowledge is and make it something more mathematically precise. That's something that's quite interesting in its own right. What does it even mean? And we're going to see what it is. Now, just for anyone who might know something about the subject, I want to clarify that what we're talking about here is technically called honest verifier perfect zero knowledge. And the term zero knowledge has many interpretations. Now, it's a subtle area, and all these definitions are quite subtle as well. One's understanding of them changes with time, going up and even sometimes going down and back again. I've been studying this for many, many years and I still get confused. It may be reassuring to see that other people also have such claims. Here's Matt Green, who's a well-known cryptographer, and he's saying on Twitter that ZK proofs are really hard. Now, I don't know if he means they're hard to understand. Maybe he doesn't mean that. He means hard to implement or design for or something like that. But it's also interesting to see, maybe to motivate thinking about and working on this a little bit more, where these things are going nowadays. So here, for example, is zero cash. This is an cryptocurrency which provides anonymity. It attempts to do a much better job at that than Bitcoin did. And it uses some very involved types of zero knowledge proofs. You can see the interest in zero knowledge in a page like this, where they effectively have all kinds of discussions about it. And this is also a cryptocurrency related thing. They call it a podcast that will go into all these things. A lot of the talks aren't directly about zero knowledge. They're more about cryptocurrency related issues. This is a group that's trying to standardize zero knowledge protocols for widespread use. So they've had many workshops and this effort is well underway. So another indication of how broad the interest is. Okay, so maybe that'll be some motivation to get into a little more of the math here. So here at the top, I just recall our protocol, right? And we're starting to think more about how we formalize and then show a claim about zero knowledge. So we've said before that the protocol is the prescribed steps for the players, the algorithms. So we'll now encapsulate that in a little bit of notation. So I'll write P and V for the prover and verifier algorithms respectively. P is just these steps and V is these steps. And now that we have those, formally zero knowledge is a property of that pair. Towards understanding what zero knowledge is, the central piece of intuition revolves around thinking about protocol transcripts. So what is the transcript? The transcript is simply all the messages exchanged. So if you give me an input n and x, and you also give me a secret little x for the prover, I can now run the protocol. And what comes out as far as the flows goes is called the transcript. At this point, I could write it as an algorithm. I don't need to have these little pictures of Peggy and Vic around. What is the algorithm? It just executes all the players' moves. Here it executes Peggy's first move. Here it executes Vic's, another move by Peggy, and that's the transcript. So I can always run this algorithm and get a transcript. Why are these transcripts interesting? First of all, notice that this transcript algorithm depends on Peggy's secret. To generate the transcript, it needed that because this flow in particular depends on that value. And that's going to be something that we'll see later. So the intuition of zero knowledge is the following. It says that the information content of the protocol is only in the transcript. What Vic learns is whatever the transcript provides. Why is that something sort of subtle and more non-trivial than it seems? Because in the actual protocol, the flows come and go in a certain order. And the transcript itself need not be generated in that order. Effectively, the claim is that the order in which the flows show up to Vic doesn't influence their information content. It's just the actual flows themselves. So let's start developing that. So we have this algorithm that generates transcripts, and we call these real transcripts because they correspond to real interaction. And recall that to do that, it needs as input the secret of the prover. So as stated, the intuition for zero knowledge is that the information is in this transcript. And the idea of the definition is that zero knowledge means that when Vic gets the transcript, he looks at it and says, this is of no use to me. Why? Because I could have just created this myself. Even if Peggy was not around, and I don't have the secret little X that she used to generate it, presumably, I don't care. I could have just created that conversation transcript without her help. So how can it possibly be of any use or be providing any information or knowledge of any value? So that's what the definition will say. And the subtle element of this, of course, is that Peggy is using a secret and something non-trivial is happening with her use of that related to other properties like soundness. But when it comes to knowledge, the only thing that matters is the content of the transcript. And the trick that will enable the verifier to make this statement true is that the order in which elements in it are generated can be changed. So to formalize this, we now have a new member of our cast of characters. As though the prover and verifier weren't enough, we have something called a simulator. This simulator, in some sense, represents something that Vic will be doing, but it's a separate algorithm. Its job is to take the input nx to the protocol, the thing over here about which the claim has been made. Notably, it does not have a secret. It kind of represents Vic, who does not know what that secret is. Nonetheless, somehow it's going to generate a transcript, even though it doesn't get the secret key as input. And the transcript should be basically the same as this one over here. So that's a little weird. How is it going to be possible for the simulator to generate a transcript when that appears to use a value that it doesn't know and has no means to easily compute? So we'll see how that might work out. First, we'll add a little bit more explanation on what we mean by saying it's the same transcript as here. After all, this process isn't deterministic. It's generating transcripts from some distribution. When we say same, what we mean is that if I generate the transcript this way or this way, nobody can tell them apart. So that's formally captured by talking of a distinguisher. A distinguisher gets a transcript as input. It also gets n and x. And it tries to tell, was it generated through this algorithm or through the simulator? And if the distinguisher says, I don't know, then our simulator is doing a good job. So our job to show that something is zero knowledge consists of exhibiting a good simulator. I have to actually show you one by writing code for it. And then also show that it fools the distinguisher in the sense that the distinguisher has no advantage in distinguishing transcripts produced by the simulator from the ones here. Okay, so we can formalize this property of what it means for the distinguisher to win a little more by writing actually a game. So having fixed the prover-verifier pair and looking at a candidate simulator, I want to talk about how I measure how well that simulator did. How do I do that? I consider a game, and that game is played by the distinguisher. It has an initialize oracle which simply picks a random challenge bit and returns nothing. And then the distinguisher can go here and say, I want a transcript. Now, interestingly, the distinguisher gets to provide a secret key for the input for which it's requesting a transcript. And it better be correct. If it is, we either generate a transcript according to the transcript generation algorithm or according to the simulator. And which choice we make depends on this challenge bit. If it's a 1, it's done this way. If it's a 0, it's done this way. And the distinguisher gets that back. Now the distinguisher tries to guess what the challenge bit is by submitting some B prime, and the game sees if it got it right. Its advantage is defined as twice the probability of winning minus 1. Again, this is scaled in such a way that if this probability is a half, this value is 0. The superscript is the metric name, ZeroKnowledge. The advantage depends on the protocol PV and the simulator and is a function of the distinguisher. Okay, that is giving us a metric for how well the simulator does. If the distinguisher has a high advantage, we have a bad simulator. If the distinguisher has a low advantage, we have a good simulator. We'll take a very extreme rendition of what it means to be good. We'll say that S is a good simulator if no matter what distinguisher you try to give, it'll have 0 advantage. So the simulator is perfect in the sense that the transcripts it creates look exactly like real ones. So now we have a formal definition of ZeroKnowledge. And having said what a good simulator is, what that definition says is that the protocol is ZeroKnowledge if you can exhibit a good simulator, one which for which every distinguisher has advantage 0. So to show ZeroKnowledge, I have to actually provide such a simulator. And also, it has to be efficient, meaning its running time can't be too big. In particular, it should be formally in complexity theoretic terms, time that's polynomial in the length of the inputs. In our case, think of something like quadratic because the main operation is modular exponentiation. Now, this is a fair amount of technical sophistication and a lot of quantifiers. You really have to go over it multiple times to understand what this means. So, assuming we've managed to do that to some extent, we can go back to a protocol and now try to exhibit simulators. How are we going to exhibit these simulators? So remember, its job is to mimic the transcript and mimic the output of the transcript generation algorithm. The difference being that this simulator is not given as input a secret key. Okay, so what does it have to actually do? Well, we need to look at all these flows and kind of regenerate them. Here's an idea. The simulator says, okay, I could just run the transcript generation algorithm. Why don't I just do that? Then of course I'll get a perfect transcript. But there's a little problem. This needs an input, which is a square root of big X, and it's not given to the simulator. So the simulator says, well, I'll just pick it. I take this set of square roots of X, and I grab a random one, and now I run the transcript generator. The difficulty here is efficiency. We had said quite a while back that a job of finding a square root of a quadratic residue is not known to be efficiently possible. It's not a known polynomial time problem or algorithm for it. So there's no way to actually do this. And so one of our conditions to make this a good simulator fails. So that's not going to work. Okay, so here's another try. What this simulator does is it starts playing the game like Peggy. It says, okay, I'll just go as far as I can and follow the steps. Pick C at random, generate the commitment to beat square. And then I notice that if the challenge was 0, I need here to provide what? Simply a square root of commit inverse. But that would just be C inverse. That tells me that if the challenge is 0, I can in fact satisfy this equation. So I set the challenge to 0, compute the correct response, and return this transcript. And indeed, the equation that we want will be true, which says that the verifier will accept. Okay, is that a good simulator? The good thing is that if we are thinking of the job of the simulator to be to return a transcript satisfying this equation, it does. We created it to do so. The difficulty is that the challenge is always 0, and that's not true here. Here it's 0 half the time and 1 half the time. So if you look at our other condition, it says no distinguisher should be able to tell these transcripts from the ones coming from the transcript algorithm. But that's going to fail. Why is that? Because these transcripts always have a 0 here, and the real ones only have that with probability half. If you want to formalize that, we could write a distinguisher. It would run its transcript oracle on some input. It can make up whatever input it wants and get a transcript. And if the challenge in that transcript is 0, then it'll say, I think I'm talking to the simulator, and otherwise it'll say, I think I have a real transcript. And it turns out that this has an advantage of a half. So not done yet. And now let's consider this one. So this is somehow brings in the real trick. The trick is that you can actually generate something perfectly correct if you change and reverse the order in which you do things. What this simulator does is it says, I will first do Vix move and pick a challenge. I haven't yet picked this. I'll pick this first. Then I'll actually go ahead and pick a response as simply a random point in Zn star. Now I'll look at things backwards and say, can I create this to satisfy the equation? But that's quite simple. You can solve this equation for commit, and you'll get that it's response to the -2 times x to the challenge. And so that's what's done here. When you return that transcript, certainly the equation is true. You can check that, but that's pretty evident from what's over here. What's more interesting is that it actually works. If you try to design a distinguisher to tell these transcripts apart from real ones, you will fail. No distinguisher can actually do that. And this is what establishes zero knowledge. So again, the bottom line is that the trick is that the simulator picks the components of the transcript out of order. First these two, and last the thing that the actual prover would have sent first. But since the information content is what's relevant for knowledge, this shows that the transcript doesn't contain any useful knowledge for the verifier. Okay, so in summary then, we now have our protocol and we have a good simulator, and we have given a definition for what it means for the protocol to be zero knowledge, and we proved that by exhibiting this simulator. So that was one example. This is a huge area. There are tons and tons of other protocols. For example, if you go to Google Scholar and you just search for papers with zero knowledge, even in just the title, you come up with 1,300 results. If you search for papers which have zero knowledge somewhere in there, you get 21,000 results. There's a massive amount of research in this area, and it's been going on for several decades now. There are many, many different types of zero knowledge. There are lots of different protocols. And nowadays, the big trend is to try to find highly efficient protocols which can be used in cryptocurrencies and other places. If you look at where this is in practice, though, it's still the case that it's a little bit limited. So when zero knowledge was invented, it was viewed as kind of solving all of cryptography and security problems. But in practice, its usage is quite limited until the recent ramp up with cryptocurrencies. It's an interesting philosophical question as to why that happens. and we can speculate. But one reason that's kind of interesting is that problems that in principle can be solved with zero knowledge often don't actually need it. There are other ways, and then you might prefer those. But nonetheless, I still think it's one of the most intriguing concepts out there, and it's really nice to know about.